We are going over tangents to a circle, 10.5, and then tomorrow is 10.6, and that's on tangents as well as what are called secants to circles, and how those all tie in with angle measures tomorrow. Today we're looking at how tangents tie into lengths, segment lengths in a circle or relating to a circle. And then 10.7 is Wednesday, and that's also going to deal with more of secants and tangents. And I will say there's a lot to keep straight with tangents and secants in terms of all of these theorem boxes you're going to see these next 3 days. These relationships are easy to get mixed up. It's very important that you're doing the practice, letting me know if you have questions, and then as we review then is going to be Thursday and Friday this week. So Wednesday is the end of chapter 10. Thursday and Friday is review. So looking back at these is going to be important as you're reviewing, and then that leaves the test Monday. I'm not a huge fan. I try not to give Monday tests, but that's when it falls. I don't want to give a third review day. That's not necessary, and I'm not going to take a review day away. So that is on Monday, and then we'll get into our next unit after chapter 10. And I do have your quizzes that I'll get back to you also. So here's where we're at with tangents. First of all, what a tangent is. You have seen the word tangent before in terms of trigonometry, like sine, cosine, and tangent with right triangle trig. Like the tangent key that's on your calculator, this is not that same tangent. So this is different. So a tangent to a circle is a line in the same plane as a circle that intersects the circle in exactly one point. And that point is called a point of tangency. And as you write that in, you can look at the diagram that's off to the right, where we have circle C. And we have line AB would be what's called a line tangent to the circle at point A. A would be the point of tangency. So it's a line that just touches a circle at one point. It doesn't actually go through the circle. It's a line that just touches a circle. So in those next set of blanks there, AB, so line AB, so with that line symbol above it, is tangent to circle C at point A. That point of tangency would be point A. And then even though a tangent is defined as a line, it can also be a segment or a ray. So segment AB and ray AB are also called tangents. And then we have what's called a common tangent, and you can kind of see some diagrams of that below. So a common tangent is a line, ray, or segment that is tangent to two circles in the same plane. So common tangent is a line, ray, or segment that is tangent to two circles in the same plane. And then there's examples there of how that can look. And so the first three examples, I should have actually had you pick up some rulers for this, so just do your best to kind of freehand it. Unless you have a ruler, you can get that out. But it says to draw in the common tangents to the circles that are given. So I'm going to look at A with you, and actually there should be a C here. There's no C. There should be a C. I'm going to look at A with you, and then I'd like you just to try B and C, and we'll kind of compare. So if I were to look at the two circles in A, you want to picture where a common tangent would be. So where a line, ray, or segment would be tangent to both circles. So in the way this is drawn, I could draw a line that would kind of go here So again, if you could kind of picture where it would be before you draw it in, and do your best just to kind of freehand it. But if that line there, so it would just touch the bigger circle here, and it would touch the smaller circle here, so it would be tangent to both circles. So one line right or segment that's tangent to both. That means there would also be another one kind of on the other side of those circles. There'd be a similar one right here, kind of at the bottom. So they might have more than one common tangent. So this one has two common tangents. Okay, so what I'd like you to do is look at B and C and think about how many common tangents there would be, and then do your best to draw or sketch those in. And you can look at the example we just did as well as the two that are above to give you an idea of what to look for. So just take a look at those and then we'll compare. It would not. So like it could look like this one does, where it's tangent to this circle here and the circle here. So it could look like that, versus it doesn't have to be like both points of tangents here on the bottom. Is that what you're asking? Yeah. Okay. So I just want to give you a chance to kind of think about what those common tangents look like, how many we would have. Draw them in. That means you want to draw all the common tangents. So for sure there's at least two. There's actually I don't have them drawn in yet. I will, but it looked like a lot of you did get all of them. B actually has 4 of them. So for B, there's 2 like this. Oops, that was not drawn the best on my part. But then there's also 2 like this. So one would go like that, and then the other way also. So there are 4 for B. C only has 1. Both circles have that same point of tangency, so the tangent line is the same, like in exactly the same place for both. So understanding what a tangent is, touches a circle at one point, common tangents, that's just understanding a tangent line to a circle. Then what I have here, the shortest distance from a tangent to the center of a circle is the radius drawn to the point of tangency. So when you're thinking about The distance from a tangent line to a center of a circle, the shortest distance is a radius from that point of tangency to the center. And that actually brings us to this first theorem. So you don't have to remember the number of the theorem, you just have to understand the theorem and how to apply it. So it says, in a plane, a line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. So a line is tangent to a circle if and only if it's perpendicular to a radius drawn to the point of tangency. So it says, as an example, to this circle, line L is tangent to circle S if and only if L and then ST are perpendicular to each other. So that if and only if statement means it goes both ways. If you know that line L, if you're given it's a tangent line and this 90-degree angle is not marked, you can draw that in if you know that line L is tangent at T. Or if you're given that this is perpendicular, but you're not told it's a tangent, you can say that it is a tangent. So that goes both ways. So how we're going to use that theorem in these first sets of examples. So it says JL is a radius of circle J, and it says determine whether KL is a tangent to circle J. So they're not telling us that it is a tangent line, we're determining if it's a tangent line. So by this theorem, it's only a tangent line if this is a 90-degree angle, but I'm not going to draw it in because we don't know that yet. If this is a 90-degree angle, that would make this a right triangle. And when you have a right triangle, Pythagorean theorem should hold true. So what I can do is I can use the Pythagorean theorem to determine this. So I can say, well, first of all, what I should do here, this 9 that is labeled is only for this. So I am not given this length here. Anyone know what this length would be? 8. It's also a radius. So that means this hypotenuse, or what we would think of as the hypotenuse if this is a right triangle, would be 17. So what I'm going to do is I'm going to determine, does 8 squared plus 15 squared actually equal, so I'm putting a question mark above it, I don't know if it does it equal 17 squared? If it does, then I know this is a right triangle. I know that JL and KL are perpendicular. I know it's a tangent. If they're not equal, then I know it's not a tangent because it's not a 90-degree angle. So 8 squared is 64. 15 squared is 225. And then 17 squared is 289. So if I add 64 plus 225, that is 289, which is equal to itself. It does work out. So therefore, I know then that this is 90 degrees. And I'm going to say yes. And I'm going to put the reason since that tells me JL, that segment JL is perpendicular to KL. That's what I just proved, that JL and KL are perpendicular by showing that was a right triangle. Since they're perpendicular by that theorem, I know KL is a tangent. So you're going to see a lot of Pythagorean theorem as we work with tangents because of that perpendicular property they have with a radius. Questions on that one? Okay, so then if we look at example 2, this one is similar. Determine whether GH is a tangent of circle F. So I'm looking to see, is angle G a 90-degree angle? And so I can set this one up very similar. This segment here, first of all, that you're not given, this length would be 6. So this FH here altogether is 18. So I'm going to look to see, does 6 squared plus 8 squared equal 18 squared. So that would be 36 plus 64. Does that equal 18 squared is 324? But 36 and 64 is 100, which is not equal to 324. So that means this is not a right angle. They're not perpendicular. So I'm going to say no, since FG, the radius FG, is not perpendicular to GH. So any that you're asked to determine, you can use Pythagorean theorem to determine that. Questions there? Okay. Then example 3 is different because you're told that JH is tangent to circle G. So when you're told that, even though it's not drawn in, I know that angle J is a 90-degree angle. So you can draw that in because you know it's already a tangent. And then it says find X, which again, you can still use Pythagorean theorem because you know you have a right triangle. Here you have to be careful though. So we have GJ is X, JH is 12. Your hypotenuse though is this X and then this 8. So all together, it is the quantity X plus 8. Okay, we can't add them together to be 8X. We have to leave it as X plus 8. So when I set up my Pythagorean theorem, I would have X squared plus 12 squared should equal this whole quantity squared. So X plus 8 in parentheses squared. And I'm solving that equation for X. So I have X squared plus 12 squared is 144. On the right side though, when you have a quantity in parentheses with a plus or minus sign, you cannot distribute that exponent to be X squared plus 8 squared. Anyone know what you have to do with this to simplify it? Do you have to what? Yes, so it's anything squared is that quantity times itself. So this represents X plus 8 times itself. I don't know if that's what you were saying, Grant, with another set of parentheses. And then how do you simplify this? How do you multiply these? FOIL it, yep. So first outside, inside, last. So I still have X squared plus 144 over here. Here I would have X times X, so X squared, X times 8, so plus 8X. That's my first outer. Inner is another 8 times X, so plus 8X. And then 8 times 8, so plus 64. And then you can simplify. So I have X squared plus 144 equals X squared plus the 8X and 8X are 16X plus 64. And now when I'm solving for X, I notice I have X squared on both sides. So if I were to get them to the same side, subtract X squared, they actually both cancel out. So I just have 144 equals 16X plus 64. And then solving for X, I would subtract 64. So that would give me 80 is equal to 16X. Divide by 16. And X is 5. Okay, so you might have problems set up that way where you have to FOIL as part of your process. Not all of them are like that necessarily, but some are. Okay, so I want you to try 3A and 3B, these next two practice problems. I want you to solve both of those. The same directions are as, for example, 3. So I know it doesn't say it here, but you're assuming the line that appears to be tangent would actually be tangent. So like CB is a tangent line in 3A, and then QS is a tangent line in 3B. And find X for both. All right, we're going to check these.
Excuse me, I'm right here.
You should have square root of 93, so approximately 9.6 or 9.64 for 3a, and then 3b, x should be 3. It is, one thing I do want to point out, because some of you did have it, when you take the square root, you do get a positive and a negative, but you can rule out the negative because x is the side length of that triangle, so x can't be a negative number, so you can rule out the negative and just give the positive. You don't have to put plus or minus. And if you still have questions on those, let me know. I'm going to just jump ahead to the last two. So here's another theorem. So 2 theorems you have to keep straight for today, and then we'll keep adding on more relationships tomorrow. So here, if you kind of look at the picture, it says if 2 segments from the same exterior point are tangent to a circle, then they are congruent. So it says if AB and CB are both tangent to circle D, then they must be congruent to each other, but only if they're both tangent. So let me just highlight this here. And that goes both ways. So if you're told they're tangent, you know they're congruent. If you know they're congruent, they must both be tangent. So it kind of goes both ways. So it says find the value of x, assume that segments that appear to be tangent are tangent. So in 4a, it does appear that RQ is tangent at Q, RS is tangent at S. That means since they both have the exterior point R, they are congruent to each other. So to find x, you can set them equal. So 3x plus 8 must equal 26, and solve for x. So subtract 8. 3x would equal 18. Divide by 3, x would equal 6. And that also goes for 4b. These appear to be tangent, therefore they must be congruent. So while I pass out the assignment, why don't you just do 4b if you haven't already. Make sure you can get the correct x value. And then I'll pass out the assignment. And you have the remaining time to work. I think you all got it, but you should have 3 for the last one.